Hello everyone. Previously on our discussion about work energy and power, we have tried to see about how to using a dot product. The dot product of force and displacement gives us mechanical work. We have also tried to see about work done by constant force and variable force. Like applied external force, frictional force and gravitational force can be categorized under constant force. We have also tried to see about work done by variable force like a spring. Today we'll try to discuss about energy. Energy is one of the entity of the universe. Universe is all associated with energy. And how do we describe energy? Well, energy is something which enables us to perform work. Especially here, we are trying to discuss about mechanical work. So, something which enables us to perform mechanical work is considered as mechanical energy. So, we are dealing all about mechanical energy here. So, the ability or the capacity of something to perform work is known to be energy. We call it to be energy. There are different forms of energy in the universe. Sound is energy, light is energy, chemical energy, electrical energy, nuclear energy, and so on. We have different forms. But we mainly focus here on mechanical forms of energy. The two types of mechanical energy are the kinetic energy and the potential energy. So we are mainly focused on these two types of energies. What is kinetic energy? Kinetic energy is a type of mechanical energy which is highly correlated with the movement of the particles, with the motion of the particles. So it's energy due to its velocity or it's energy due to its motion. So that it's stated as, suppose this particle is moving from this to this point, and there might be a change of velocity as it moves from this to this. As we exert a force, there will be acceleration, there will be a change of velocity. We know that from your kinematics concept, V final squared is equals to V initial squared plus 2AS. You have this kinematics equation. So V final squared is equals to V initial squared plus 2AS. When you move this velocity initial in this direction and put here 2 V final squared minus V initial squared over 2 is A times S. Now let's try to multiply both sides by mass M. When you try to multiply by mass m, V final squared minus V initial squared, and for acceleration times displacement as well, mass times acceleration times displacement S here. Mass times acceleration is known to be force, okay? And here you have displacement. Force times displacement, we have previously mentioned that it is work, okay? We have work. Then it tells us that work is equals to, on the right side or on the left side of this, we can rearrange those things, 1 over 2 m the final velocity squared minus 1 over 2 m the initial velocity squared. Now the quantity on the left side of the equal sign, which is the product of 1 over 2 mv squared, enables us to perform work. The change of something enables us to perform work. What is that? The ability or the capacity to perform work is known to be energy. So what kind of energy is this? And this is energy due to motion of the particle or energy due to the velocity of the particle. Therefore, this is what we call kinetic energy. Therefore, the product of 1 over 2 mass times velocity in general squared is called kinetic energy. It's all energy due to the velocity v. And 1 over 2 mv final squared is known to be kinetic energy final due to the final velocity, and this one is the initial kinetic energy. Therefore, the difference in kinetic energy enables us to perform mechanical work. This is the first form of energy due to motion. And the other thing is energy due to change of position is known to be potential energy. We'll try to see about that. Here, the final kinetic energy minus the initial kinetic energy is given to be the change of kinetic energy. It's possible to rewrite this as change of kinetic energy. Work can be associated with a difference in energy. The difference in energy due to motion is kinetic energy. The change of kinetic energy is equals to work. This is what we call the WorkEnergy Theorem, the WorkEnergy principle. The WorkEnergy Theorem states that the work kinetic energy states that it's possible to correlate work as equals to the change of kinetic energy. This is what it says. Okay, here you have the WorkEnergy Theorem, work kinetic energy theorem. Let's try to solve one good example. What is the kinetic energy possessed by 4 kilogram objects as its speed is exactly 6 meters? Suppose a given object is in a state of motion, so that what is its kinetic energy at instant time t as the velocity v is 6 meters per second. Well, it's so easy and direct forward. So kinetic energy is 1 over 2 mv squared. 1 over 2, mass is 4 and the speed is 6 squared. So when you multiply this, you can find that the kinetic energy is 72 joule. By the way, the SI unit of energy and the SI unit of work are all the same, joule. The SI unit of energy, any form of energy, is joule. Sometimes they might be different units, like for heat, you might use calorie, but there is a relation that 1 calorie is 4.2 joule. And for in electricity or in atomic physics, you might use electron volt. Electron volt is the other unit of joule, the other unit of energy, but the standard unit is always joule. Joule is a unit for energy and for work. Okay. Now, WorkEnergy Theorem states that the case in which work is done on a given system, the change in its speed enables us to perform work. And that is what you call WorkEnergy Theorem. The final kinetic energy minus the initial kinetic energy is equals to work. Change of kinetic energy is equals to work. Let's try to apply the WorkEnergy Theorem to solve this example. What is the final speed of the previous 4 kilogram mass if its initial speed is 6 meters per second? Its initial speed is 2 meters per second. As 42 joule of mechanical work is performed on it. Let's try to apply WorkEnergy Theorem. We know that work is equals to 1 over 2 mv final squared minus 1 over 2 mv initial squared. So we are trying to determine the final velocity or the final speed of the particle, as there are 42 joule of mechanical work is applied on that object. Therefore, to find the final velocity, WorkEnergy Theorem states that work is equals to the change of kinetic energy. The final velocity can be given as, when you shift this to work, it becomes positive. This is negative, when it comes here positive. Work plus 1 over 2, the initial velocity squared gives us 1 over 2 mv final squared. Therefore, substituting all those quantities, it's possible to have 42 plus 1 over 2. The mass of the particle is 4. The initial velocity is 2. 2 squared, 1 over 2. Again, the mass of the particle is 4 kilogram. Rearrange, you can find the final velocity is 25. So, square root of 25, when you squared both sides, it gives us the final velocity of the particle becomes 5 meters per second. Therefore, you can possibly substitute and apply WorkEnergy Theorem to solve such kinds of problems. The other form of energy is potential energy. Potential energy is a type of energy due to the change of position or change of shape. Like spring, if you compress it, you are changing the position. Or if you are trying to move one object from a certain height to another height, from a certain elevation to another elevation, you are performing or you are storing energy, and that energy is known to be potential energy. Suppose here this object is moving from point A to point B, or from this point to this point, a different elevation. You can shift this way or this way. There will be a change of position. Due to that change of position, there will be a work performed on it. And the change of something enables us to perform work, and that is energy. And the type of energy here is known to be potential energy. Potential energy can be categorized into two, as gravitational potential energy and elastic potential energy. Actually, there are different types of potential energy. Like if you are in electricity, you have electrical potential energy. If you are in nuclear branch, nuclear potential energy. There might be different potential energy. But under mechanics, we mainly focus on gravitational potential energy and elastic potential energy. So first, let's try to see about gravitational potential energy. We know that Here, as this object is moving from this to this, let's say it's moving downward, we are having mg, we can have mg. The object, as the object is moving downward, from this point to this point, there will be a displacement, okay? And that displacement can be given as change in height. Change in height. Change in height means the initial location of this particle can be given as HB, the initial location of B, and this is said to be HA. If it is expressed like this, the difference between HB and HA is known to be change in H. We can express this as change in H. Change in H is H, the final height, HA minus HB. You can find that H. So this is the displacement S. And we know that work can be given as force times displacement. Force times displacement times cos theta. In this case, as object is moving downward, the displacement is also downward. Theta is 0. If it is moving upward, mg is acting downward, the displacement is moving upward. You can take 180. Okay, if you take from this to this or to this, has no difference. Therefore, we can apply, for example, if it is moving from A to B, cosine of 180 gives you -1. You can have the negative of mg. Work done against gravity. Since you are moving upward, you are performing work against gravity. In this case, mg, the force exerted is due to the weight of the object, mg. HB minus HA, when you are trying to multiply here, mgh B at location B minus mg HA at different location. Look here, you are performing work. How and why are you performing work? Because there is a difference of something. And what is that difference? The difference in elevation. And the difference in elevation enables you to perform work. The ability and the capacity to do work is known to be energy. So the energy which appears due to the change of position is known to be potential energy, gravitational potential energy in this case. Previously, the ability to perform work is due to the change of velocity. That energy is known to be kinetic energy. But here, the change of position tells you how to perform the potential energy, and it's known to be gravitational potential energy. The object might move again downward. It's also possible to take it downward so that you can have mgh at B minus mgh at A. This is what we call work done by potential energy. And the work done by the negative potential energy is always given to be the negative of change in U. Work done by potential energy means gravitational as well as elastic, or generally you can consider them to be conservative, can be given as the negative of change in U. Because here mgh, the height at B and the height at A, when you are taking the difference h at B minus h at A, gives you negative. Okay, it always gives us negative. When you are trying to move against the gravity, it's also negative for the above case. The other form of energy is elastic potential energy. Previously, we have seen about gravitational potential energy. Now, we can have elastic potential energy. Elastic potential energy is all energy exerted due to the elastic materials like spring, polyethylene, and so on. So as you exert to try to pull this or try to compress this, you can restore energy on those springs. As you store or as you compress here, this spring has energy, the potential energy to exert force. So such type of energy is known to be elastic potential energy. If you are trying to pull this and release it suddenly, there will be performance of work as it tries to pull this mass along this side. So this type of energy is known to be elastic potential energy. And elastic potential energy is mathematically given to be 1/2. Here you have the work done by the spring. You can say spring or any other elastic material can generally be given as minus 1/2 kx squared. We can have it to be minus, actually for this case it's not minus. For a work done to be work done by the spring can be given as 1/2 kx squared. Previously we have seen this. Work done by the spring can be given as plus or minus 1/2 kx squared. But for elastic potential energy, the energy, there is no negative energy. Actually, if you find the negative means, it means something out or in. But energy on a spring is always given to be 1 over 2 kx squared. The elastic potential energy can be given as 1 over 2 kx squared. We have classified potential energy into two as gravitational and elastic. Gravitational potential energy can be given as mgh. This is how we determine. Kinetic energy can be given as 1 over 2 kx squared. And the elastic potential energy can be given as 1 over 2 kx squared. We can summarize it here. Kinetic energy is generally given as 1 over 2 mv squared. Whereas potential energy is categorized into two as gravitational and elastic potential energy. Gravitational potential energy is mgh, whereas the elastic potential energy can be given as 1 over 2 kx squared. So these are the forms of energy that we mainly focus. The difference of those energy enables us to perform work. In this case, we have seen WorkEnergy Theorem that the total work done is the change of kinetic energy. But in this case, these two are known to be the potential energy, work done by the potential energy. Previously, we have said that gravitational and elastic materials are said to be work force on elastic substances are said to be conservatives. So therefore, work done by conservatives can be given as the negative of change of potential energy. So we can equate these two equations and find a very important expression and a very important law, the law of conservation of mechanical energy. And that is the total work done from WorkEnergy Theorem says that the total work done is change of kinetic energy. What does it mean by change of kinetic energy? The total work done is the work done either by conservative force or the work done by non-conservative force. There might be non-conservative force like frictional force and so on. So work done by conservative force plus work done by conservative force and non-conservative or dissipative force generally gives us the change in kinetic energy. Sometimes if there is no conservative force, the work done by non-conservatives is the change of kinetic energy. If there is no non-conservative force, the work done by conservatives can give us the change in kinetic energy. The same of these two can also be given as the change of kinetic energy. And here we have work done by conservatives. And the work done by conservatives can be given as negative of potential energy. So that we can have the conservation of mechanical energy. Here, work done by conservatives and non-conservatives is generally changing kinetic energy from WorkEnergy Theorem. Therefore, when you substitute that work done by conservatives, like gravitational and elastic materials is a negative of potential energy, you can substitute here. Okay? When you substitute here, then negative of potential energy plus work done by non-conservatives is equals to change of kinetic energy. When you transfer it here, work done by non-conservatives gives you the change in kinetic energy plus the change in potential energy. The change of potential energy, the summation of kinetic energy and potential energy is known to be mechanical energy. Therefore, generally, we can have work done by non-conservatives force is equals to change of mechanical energy. This is the other equation, very important equation. Work done by non-conservative means work done by dissipative force, work done by frictional force, and the like. So in this case, for example, work done by non-conservatives is equals to the change of mechanical energy. Mechanical energy final minus mechanical energy initial. If you are transferring this in this side, you can have mechanical energy initial plus work done by non-conservatives is equals to mechanical energy final. Okay? This is a very important equation. If there is no frictional force, the work done by non-conservative force becomes zero. If there is no work done by frictional force. If work done by non-conservative force is zero, you can possibly say that the initial mechanical energy and the final mechanical energy are equal. So mechanical energy initial is equals to mechanical energy final. By this, it's possible to say the law of conservation of mechanical energy. So for the cases where there is no dissipative forces, mechanical energy is always constant. If there are dissipative force, if there are force like frictional force, you should have to use the mechanical energy initial plus work done by non-conservative, meaning work done by like frictional force is negative work done. When you subtract these two, you can find or equate it with that of the final kinetic energy. So here we can have different examples. Students, please try to this with concepts that I have already provided you. Please try to solve those examples. There are two cases. One, the block is moving on a frictionless block, and the other concept is while it's moving with friction F and having a coefficient of friction 0.2. Please try to solve this. And this is all that I have got for today. I think we have some limitation of time. I'm trying to be faster so that you can have the main points. Next time we'll try to see other topics. Bye bye for today.